start today's lesson, because today's lesson is quite short, about 1.5 hours. I might extend a bit just to make sure I cover as much as I can. All right, so welcome to this, welcome to OVERMUGGED, this WA1 online revision that we have for our student and also for the public lah, in this case. All right. Okay, so okay, more people are coming in. All right, so just a quick introduction to myself. So my name is Dr. Shafiq. Actually, I've been with OVERMUGGED for only a few months. All right, but I've been teaching chemistry for a very long time. I mostly teach JC chemistry, but of course, from time to time I do help with the O-level chemistry side also lah. All right, so these are my credentials and journey with chemistry lah. All right, so I did graduate with a chemistry degree and PhD. All right, so as you all know by now, we have about 7 branches across Singapore. We do cover north, south, east, west, and the central. If you're interested to find us, these are the locations that we have. All right, and then yeah, we have about currently about across our center about 5,000 students in past and present lah. Okay, so our students are usually achieving quite well for their national exam, and this is because we are driven. Our tutors are all driven lah. All right, so we are quite experts in our field. And just to let you all know, what are some of the resources that we have? We do provide very detailed curated notes. We do provide weighted assessment revision like today also. All right, mock exam from time to time nearing your exam, national exam or prelim. All right, for secondary school side, sometimes we do provide science practical sessions for students. All right, so that they can at least have hands-on before their exam, and some cheat sheet. And also we allow some class consultation lah, after class in this case. Okay, all right, hold on, Angel. Okay, all right. So today, right, just to give you all a heads up for what is our plan for today. All right. So because it's only a short 1.5 hour lesson, so and we are covering about 2 topics, right? So we will try to spearhead through the content. All right. But of course, the more important one today, I want to cover I think most of the time that your school teachers like to test are these concepts that. So for separation technique, they like to test questions on evaporation and crystallization, simple distillation versus fractional distillation, and chromatography. So we will focus mostly on that. But of course, I will try to cover the rest, but it will be more of a touch and go, because I think it's quite straightforward. Most of you understand the principle behind those separation technique. All right. Then for kinetic theory, I think most likely we will cover all of the concept, but of course, I will emphasize some of the more important learning concept that you all need to know for this concept. All right. So for those who just joined in, let me show again the QR code. All right. So I will give about 1 minute or 2 minutes for you all to actually scan the QR code. Have the lesson material ready, either in the soft copy or hard copy version. Okay. So everyone who just joined in, about 1 minute or so to scan. Or you can click the link that I'm going to send in the group chat also. Again, okay? Right, so 1 minute. So for those who are done, can you all give me a thumbs up? Just to get a feeling that everyone has gotten their material. Okay, just thumbs up for me. Okay, okay, very good, very good. Thank you so much. Thank you so much. Okay, thank you, thank you. Okay, okay, thank you. All right, so I presume that everyone has their materials ready already. Okay, I hope. Okay, all right. So, okay, so for me, right, just to kind of give you a heads up for today's lesson, so here is my notes for all of you. So I will actually ask questions from time to time. I'm not going to be too often for today's lesson because the lesson is a bit too short. But if let's say I do ask a question, I direct it to you, just unmute yourself and answer the questions lah. Okay, all right. But of course, for all of you, if you have any questions during the course of the lesson, please feel free to message me on the Zoom chat. All right, I will address your question accordingly lah. Okay, all right. So don't be afraid to ask. I'm more than happy to answer your question. Okay, so let me share my iPad screen. All right, so let me go ahead and share. All right. All right. So I think most of you are here because you need some form of revision for your upcoming WA1. If I'm not wrong, I think it is the next few weeks or so that is your WA1 now. All right. And the topics we're going to cover today is separation technique and kinetic theory, particle theory in this case. All right. So let's officially start on separation technique. Now, before I officially start on separation technique, let me revise with you what are the things you need to take note about separation technique. Now, for separation technique, right, the aim of separation technique is, of course, it is to separate mixtures lah. All right, as you all know, mixtures, as if you recall what you learned probably in lower sec, right, it is made out of two or more substances that are not chemically combined with each other, right? So it's like simple as like adding sand and water, as simple as adding your sugar with water or salt with water, right? So mixtures are made out of two or more substances not chemically combined with each other. All right. So for someone who just came in, let me send the link again to you just in case you need the notes. All right. If you have not received the link to the note, two or more substances not chemically combined. Now, unfortunately for all of you, right, what happened is that you will encounter different kind of mixtures, right? So let me give you all some example of mixtures. One kind of mixture, it will be the solid kind. Another mixture you will encounter is the solid liquid kind. And the last one you will encounter is liquid kind. All right. So for your syllabus, you just need to know this few. All right. How do you separate mixtures from this kind of scenario? Solid, liquid, and liquid in this case. All right. So let me quickly run through with you some of the very classic cases of how do you separate the different mixtures here. All right. So for the pure chem student, you realize I have written whether is it for pure chem only. For the combined science student, right, you can just take note. O-level have never tested this before, and it's also in the syllabus. They written it clearly lah. Okay, it's not in the syllabus, so please take note lah. Okay, so for solid mixture, right, very simple. One way is what happen if, let's say, you have a metal that is actually can be attracted to magnets. So if you have a mixture that contain a metal like iron, iron, as you all know by now, it is a very good magnetic material, can be attracted by magnet. So metals like cobalt, iron, nickel, and steel, you can just use a magnet to just separate it. Very simple. But think sulfur, right? For those who are very familiar or not very familiar, also I can understand. Sulfur is actually a non-metal. All right, so non-metals, they will not be attracted to magnet in this case. Okay, so think so we can separate the iron from the sulfur by using a magnet. Okay, now, but let's take a look at other cases where there is also solid. Like for example, right, this one. This classic example is what we call sublimation in this case. Now, for some of you, you all learned that sublimation is a process where it will convert from solid to gas directly. All right? So it doesn't even convert to liquid in the first place. Solid straight away to gases in this case. Right now, one of the very good examples that you might have seen on a daily basis, right? So if you have buy, let's say, ice cream cake from Swensen, you might have seen, right, they place some what we call dry ice. Think, dry ice is actually solid carbon dioxide actually. So when you use the dry ice, right, it will be in the solid form. But then if let's say you throw it into water, right, if you have seen some video, I throw into water, it will turn into gas almost immediately. All right. So these are some examples that you need to know that can be sublime. So let's say iodine, mothball, and ammonium chloride. Very classic example. So meaning if you look at this diagram here, I have a mixture of, oh, sorry, there's a typo here. It should be a mixture of iodine. Okay. So everyone think is iodine here and sand. Now, what happened here? Sand, as you all know, if you go to the beach or if you have, in Singapore, there's a lot of sand, right? Sand cannot evaporate that easily. Even if you heat, cannot evaporate. But what happened to the iodine? When you heat it gently here, when you heat it, the iodine will start to vaporize. So it becomes iodine gas. All right. So let me don't write in short form. Okay, iodine gas. Then what happened? You need to put this very famous inverted funnel. This inverted funnel, what happened? It is used to provide a very cool surface for the iodine gas to actually condense on it. So, can everyone take note? Is to provide a cool surface for the iodine to condense. Then what happened? You can see the iodine will be all collected here. Then what happened? We can just, after that, it's already essentially separated lah. So the filter funnel or the inverted funnel here will have all the iodine. Then what you are left inside this crucible, right, is actually just your normal sand. That's it. All right. That's the easiest way to separate the two of them. Okay. So that's pretty much it. So you can read through the procedure. The procedure is whatever I have mentioned just now lah. Right. So you just need to gently heat, place the inverted funnel, and then you let it condense lah. And that's pretty much it for this part. All right. Now, so this is what I want to go through. Then of course, what happens if let's say you're dealing with solid and liquid. Now, for solid and liquid, for those that cannot dissolve in water, for example, like your sand, you can just use a filtration method. So everything cannot dissolve, insoluble, like sand, right? So when you do filtration, what happens? The sand will get stuck here. The water will pass through. And the water will be called a filtrate, while the sand that is stuck on the filter funnel will be called a residue in this case, right? And that's pretty much it. I think most of you are quite familiar with filtration in this case. All right, so today, right, the most important thing I want to talk about is the what if, let's say, right, the solid can dissolve in water, right? So then the question is, how do you obtain the solid then if it's soluble in water? So there are two methods you can do. Either we do it by evaporation to dryness, or we can do it by crystallization in this case. Okay, so maybe now is a time for me to ask question. Okay, just to kind of give you your idea what you all learn. Maybe can I ask who's on my list? Maybe I ask Alicia. Alicia, can I ask you what's the difference between evaporation to dryness and crystallization? Okay, is Alicia there? Hello, Alicia. Oh, Alicia is not there. Okay, maybe I will ask Ellie. Is Ellie there? Okay, sorry, please unmute yourself. Ellie? Is Ellie there? Oh no. Okay, never mind. Okay, so let me address the question. So sorry, I need you all to unmute yourself to answer my question. Okay, so the difference between evaporation to dryness and what's called crystallization, right? Take note, evaporation to dryness, the word dryness means you dry, essentially you remove all the water present inside the solution. So everything else, dryness means you get rid or remove all the water. Remove all water in the solution. Okay, but crystallization, right? Take note, you will leave only a bit of water only, and later we will address that part lah. Okay, so heating till dryness, right? For the experimental setup, if let's say your exam question asks you to draw a setup, very simple. You have an evaporating dish here. You can put the solution inside. Then take note, you must put a tripod stand and then a Bunsen burner to heat it. So you heat it until all the water is gone, right? So let's say all the water gone. And what you are left at the end of the day is just the solid crystals. Okay. All right. So dry means no water. It's just solid. Solid. Okay. All right. Now, so take note why we use evaporation to dryness for only certain cases. Now, the cases that you all need to know for all of you is just to obtain your normal table salt from seawater. All right. So your table salt, the salt that you eat almost every day that give you the salty taste, right? You will obtain it by doing evaporation to dryness. Now, why your table salt often used by evaporation for dryness, right? Is because take note, they do not decompose upon heating. This is very, very important. Meaning if I accidentally maybe I forgot about the setup, right, or the experiment. Maybe the Bunsen burner is still here, still heating the solid, right? The solid will not decompose, right? So the solid is still stable. It will not decompose. It will remain as your table salt. Now, but of course, right, if you remember, right, there are some substances, right, if let's say, once you touch heat, it will start to melt, it will start to decompose in this case. And one example will be like your sugar. So if you didn't know, sugar, right, if you melt it, it becomes caramel. All right, if you didn't know that, your caramel is actually sugar. And then what happens? If you heat it further, your caramel will actually decompose to become a black solid. So that's why for cases where it is not very stable to heat, you must always use crystallization. Crystallization would be the safest method. Okay, safest method in this case. Okay. All right. So that will be the best method lah. Okay. So, but here, let me clarify a few things about crystallization. Crystallization, as I mentioned, you cannot heat until very, very dry. Maybe you heat until, let's say, left a bit of water only, like that. Okay. So, what do we call this kind of solution where there's only very little of water? We will call this a saturated solution. Take note. Okay, so I think I wrote at the bottom what is the idea of saturated. Saturated means it contains the maximum amount you can dissolve in that particular solvent or solution. So what happened, right? Because the solid here inside, right? Maybe you dissolve 10 grams of it inside. Okay, 10 grams of the solid inside. What happened? When you heat up the water, it is still 10 grams inside. It's just that now water very little. So that's why what happened after that, right? When you cool it, the crystals will start to form. That is how you obtain your solid by crystallization in this case. You heat until very little water and then you allow it to cool eventually. Okay, so as what I wrote here, it is to obtain, let's say, cases like sugar from sugar solution in this case. All right, so now this one, I want you all to put a star. Very, 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 very important. This one, because why? They like to ask questions like, how do you obtain your sugar crystals from your sugar solution? Then, of course, that means you need to explain to me the crystallization process, which is what you need to write here. Usually, this process is about 3 marks by itself. So make sure you all hit the points required to explain the separation technique of crystallization. Okay, so take note, first step, what you need to say. You need to say, firstly, heat the solution till saturated. Okay, that's the first thing you must say. After that, you say, allow the hot saturated solution to cool. Okay, the cooling part is important. To allow the formation of crystals. All right, which is what I mentioned just now. You allow it to cool, you form the crystals. All right. Now, the question that becomes, a lot of students will ask me, then how do you obtain the crystal? Because crystal still got a bit of the water, right? So the next thing you need to do is you need to filter. Don't forget to filter the mixture. Because technically it's still a mixture. You have one solid here and one liquid. You need to separate. So how? You filter. So when you filter, please take note, what happened? Your separation technique set up, filtration looks like this. So where does the solid get collected? It is going to be collected here as your residue. So you must say filter to collect the crystal as residue. You must say this. Okay. And then at the end of the day, what happened? So this residue, right, maybe not the, what is it called? Not the purest, because maybe you got some of the liquid stuck inside the filter paper, right? After that, don't forget, wash the crystal with a little whole distilled water. All right. And then after that, make sure pat dry between filter papers. Okay. All right. Someone just joined. Hold on. All right. So for the student who just joined in, I will send again the material, the link to the materials so that you have access to it. All right. So anyone got any questions with regards to the steps for crystallization? Okay, please raise your questions right now. All right. So make sure you will be able to answer this kind of question, 3 marks. All right, very good. Okay, so no questions. So let's move on to another thing. Okay, so now let me go through all what's the word next to filter paper? Is it this is between, my short form. Between, okay. Okay, so for the pure chem students, please take note, there's a few things that they also can test about crystallization. Now, the very common question they like to test it is actually about your solubility graph. I'm not sure whether the pure chem students have seen it. For the combined science, you can take note of it lah. Because sometimes they do, sometimes they don't, depending on your teachers, right? Whether they want to test it or not to make you think a bit more lah. Okay. Now, so the thing is that what is this solubility table? So imagine, let's say I have a solid, right? Okay. Okay. So let's say I draw for you the graph. Solubility, maybe solubility. Let me write gram per 100 cm cube. And then this is the temperature. All right. Now, what kind of solids are able to you can crystallize by using this method, right? Is this kind of case, right? The solubility curve look like a really, really very nice curve like this. Why? Why is it important to know this, right? It's because let's say, for example, when you were heating it during the saturation process, right? Maybe the solid okay, maybe let's say I write 80 degree, you heat until 80 degree, right? This is the amount of solid that can dissolve. Maybe let's say I give a number 80 gram, for example. All right. Oh, someone just came in. Okay, hold on. Okay, 80 gram. But remember just now I mentioned, right? After you heat, you will let it cool. You will cool it to, let's say, maybe 20 degree, for example, right? So after you let it cool, okay. So after you let it cool, right? What happened? Maybe let me show 20 degree maybe only 40 gram can only dissolve. So what happened, right, is that what is the thing that you all must take note? The difference from 80 to 40, right? That means 40 gram of the solid will actually crystallize. So that is the idea of crystallization. So you start off with 80, but then only 40 will remain dissolved inside the solution or water when you cool it. So the remaining 40, what happened to it? It will just become crystal. Yeah. So just to let you all know, crystallization may not be the perfect case because you see, you start with 80, but you only gain back 40. Then what happened? The remaining 40 will remain dissolved in the solution. So it will still remain. So we cannot obtain all the 100% 80 gram in this case. So this is something for all of you to take note. Okay. So compounds or substance that have this kind of graph, right, can dissolve, can obtain by crystallization. But if you have another graph like this, very nice straight line, like that, cannot. Because why? Very little you can obtain at the end of the day. Maybe 80, this one maybe 50 gram, but at 20, only 45 gram. Means you can only obtain 5 gram. Not very good. So this one not good, but this kind of case good. Okay, so for you all to take note lah. All right, anyone got any clarification? Want to ask about the solubility curve? All right, so that's it for evaporation and crystallization. So crystallization, they always like to ask about the procedure. So make sure you all know the procedure very, very, very well in this case. How do you obtain the sample, the crystals? Okay, so that's it for the solid and the liquid mixture. So now we will dive in. What if, let's say, you have a liquid-liquid mixture? Oh, so Jesslyn, in this case, I'm just giving you some numbers lah. So you can see what happened, right, is that let's say assuming 80 degree, 80 gram can dissolve. All right. But let's say maybe we cool it to 20 degree, like room temperature, right? You only can get only 40 can dissolve. Meaning at the end of the day, the difference, right, will be the amount of solid that will crystallize, will appear as solid at the end of the day. So I'm just giving you some examples, numbers. These numbers may not apply for every solid lah. Okay. All right. Angel asks, what type of question can they ask? Oh, okay, good question. Angel asks, right, what kind of question they can ask for solubility graph, right? They will ask you, I have seen like a MCQ question, right? They ask which graph or which substance, right, cannot be obtained by crystallization. So meaning if you choose the black line, this is the answer. This one, the one that cannot obtain by crystallization, not very good. But if you get this kind of curve, it's good in this case. Okay. All right, Ken, any questions? Anyone? Structured question, maybe just a bit of calculation, which is what I did here. 80 minus 40, then they will ask you how much solid crystallized. 40 gram, that's all. They don't really ask too much as a structured question. Okay. All right. I hope that clarifies your questions. Okay, very good. Okay, so that's it. Moving on to the last part of the separation technique. Okay, so for your separation technique, right, the last one is, of course, the very famous one. What if, let's say, it's a mixture of liquids, all right? So far, we only look at solid, and solid liquid. Now, if let's say you have a mixture of liquids, then there's also another set of ways of doing separation technique. Okay, now, so the important one that I want to discuss today is, of course, the very important one, simple versus fractional distillation. Now, this is where I think some students, if they are familiar with it, they know this very well. But for some students who don't really understand what's the difference, right? So this is a good time to actually go through what are the things you need to take note. Okay, so let's go through liquid, which is simple distillation. Now, take note, simple distillation, right? One of the very classic example would be to obtain pure water from salt or seawater. So in Singapore, we do have some distillation or desalination plant that allows you to remove the salt and to obtain pure water in this case. All right. So this is how you obtain pure water. So think, depending on the question, if your aim is to obtain the salt, right, in seawater, you must do evaporation. But if your aim is to get water, then you must use distillation in this case. Okay, so let me go through what are some features of your distillation setup. So your distillation setup, usually you have this what we call a round bottom flask. All right, and sometimes in some of your notes, you might see, right, they put some boiling chip inside. So can everyone take note? They might put some boiling chips. Okay, all right, and then important, there must be a thermometer in your experiment setup. This what we call a condenser. And then, of course, at the end of the day, you must have either a beaker or a flask to collect the water that you have obtained. So take note, the liquid that you obtain here will be called a distillate. That is the proper term you will use. Okay, it's called distillate. Okay, all right. So these are the important features. So your O-level or your exam question will ask you a few things. Number one, they will ask you, what is the purpose of the boiling chip? Okay, so now I want everyone in the group chat, right, type for me, what is the purpose of the boiling chip? Come, give about 1 minute. Everyone check whether you know your stuff or not. Okay, very good, Jaslyn. Yep. Okay, very good. Everyone gave me the correct answer. Now, so take note for your exam, you can just say, oh, to ensure smooth boiling lah. Okay, that's the answer, smooth boiling. But of course, right, student will ask me, what do I mean by smooth boiling? It's because take note, when you boil water, as you have seen before, when you boil water, a lot of bubbling, right? So this bubbling, right, what happened? It might cause the what's called this flask, right, to topple. All right, so we don't want that, right? So that's why the boiling chip is to ensure that the flask remain in its position in this case. Okay, so vigorous bubbling can cause the flask to topple. Flask to topple in this case. Okay, we do not want that. Okay, now the question then becomes, so everyone please write in also, what do you think is the purpose of the thermometer? Okay, give about 1 minute. Everyone can type in. What do you think is the purpose of thermometer? Anyone know? Okay, yep. Avilia, correct. Jaslyn, yep. Yep. Okay, Jaslyn also correct. Okay. Okay, very good. Everyone managed to give me the correct answer. So the thing is that what happened? Remember, this is, let's say, for example, is your seawater or your salt water, right? So what happened is that your water will be the first one to evaporate or boil off, right? So water will come up. Now, what happened? The purpose of the thermometer is to make sure the right thing come out from the flask. So as you all know, water boiling point is 100, right? So the thermometer should register 100. If it registers something else, means something is wrong. Okay, just to let you all know. Okay, so water, as you all know, boiling point 100. So the thermometer should read 100 degree. So the purpose of the thermometer is to measure the boiling point of the vapor that is leaving the flask in this case. All right. Okay, so that's the second question. Okay, now the third question, as you can see, if you look at the condenser, what's the purpose of the condenser? I think you all should know by now, is to condense the gas back to liquid. All right. So condenser is, oops, sorry. Hold on. Condenser is to convert or condense the vapor back to liquid. Okay. Now, there is an important question they will always ask you is, why the water must come in from the bottom, then water come out from the top? So anyone can give me an answer. Come, type for me. Why the water must come in from the bottom? It's not very important. Okay, Jocelyn, okay. Yep. Okay. Anyone else? Okay. Okay, Chloe, oh, yep. Okay, yeah. Okay. So I think most of you generally maximum cooling efficiency, correct. Okay, so most of you understand the idea of what's called why we water must come in from the bottom, right? Now, so some students will ask me, so what does it make a difference if the water come from the top? It does actually, just to let you all know. Right. So a lot of you gave me the same general idea, and that is to ensure maximum efficiency or efficient condensation of all the vapor back to the liquid in this case. So that is the standard answer we will always give lah. Efficient condensation or maximum condensation in this case. Okay, now, but let me give you some analogy lah, so that you all can at least understand what is happening here. So imagine, let's say, if you want to fill up a bucket of water. Okay, a bucket with water. Oh, sorry, someone just joined in. Hold on. Okay, now, let's say you want to fill up the bucket, right? Let's say now I fill up from the top, right? So imagine you fill up from the top, but there's a hole at the bottom. All right, let's say a hole. Now, when you fill up the bucket, you will realize, right, what happened? As you fill up the bucket, water will leak out from here, correct? Now, the question will be, will the condenser will be completely filled, like in this scenario? The answer is no. Because why? What happened is that you will constantly have something leaking out. That's why we prefer, imagine you have a hole at the bottom, but you fill it up from the bottom, so that the water will keep rising and fill up the whole condenser. So that's why we make sure it's at the bottom, because it is to ensure that the condenser is completely filled throughout the whole distillation process in this case. Okay. All right. So that is something for you all to take note lah. Why we fill up from the bottom. Okay. In this case. Yulin asked if the distillator is collected, will the temperature continue to rise up? It is possible, but then it's not the temperature or the thermometer will not be registering the vapor that is leaving. More likely, what happened, right? Maybe after you remove all the water, right, you are left with only the solid. So there shouldn't be anything else left. I mean, that can come up. Okay, hold on. Vernice is asking to share. Give me a minute. All right, so you should left the solid. The solid should not evaporate here. Okay, so let me share to Vernice here. Everything. Okay. Okay, anyone got any other questions want to ask about distillation? Okay, everyone okay? Distillation okay? Okay, that's it for distillation. So distillation are very good. Your aim maybe is to obtain water from your salt water, seawater, right? Now, but you will realize, right, your exam question, right, sometimes they like to test is the fractional distillation. Fractional distillation is the one that most teachers like to test. I just let you all know. Okay. Now, so obviously the question is, what's the difference, right, between a simple versus a fractional distillation? As you can clearly see, there is this additional part here, right? This part. Okay, someone just came in. Hold on. Okay, let me share the materials again. Okay, so this thing that you see here is what we call your fractionating column. All right, so fractionating column. Hold on. Justin asked, is it for immiscible mixture, right? Then, okay, Justin asked for simple distillation, is it for immiscible mixture? Actually, it's for miscible mixture also, technically, because, right, let's say salt and water, right, they can mix. If they can mix, right, they are technically a mixture that is actually something like what we call a solution. So just be a bit careful in this case. All right. So this one, right, for fractional distillation, right, what is it for? As what Jaslyn was pointing out to me, This is for miscible liquids of different boiling point. So for fractional distillation, right, there are two criteria. Number one, they must be miscible liquid. Miscible means they are liquids that are able to mix together. So this one a bit different from the distillation because right, for salt water is solid dissolved in water. But fractional, it is meant for liquid mixed with liquid. That's why it is miscible. So one of the classic example that you all need to know is ethanol and water. This one is the very favorite one we always test, ethanol and water mixture. Okay, and second criteria is they must have different boiling point. Very important. So what happened? Ethanol boiling point, very well known, is 78. Water boiling point is about 100 degrees actually. Oh, wait, someone just came in again. Hold on. Okay, so let me repeat. For fractional distillation, it is to separate number one, miscible liquids, means can mix together very well. And number two, different boiling point. So ethanol and water, right? I think you have seen before this kind of mixture, right? I hope lah. Okay. One example will be like, say for example, like your last time during the COVID period, it is your hand sanitizer. All right. All right, hand sanitizer. And then of course, some other cases would be, let's say, your alcoholic beverages like beer and stuff. They all contain ethanol and water in this case. Simple distillation is possible for immiscible and miscible liquid. Yes, Angel. Yeah, you are. Okay, wait. So, Angel, actually, yeah, immiscible liquid not possible for simple distillation. Yeah, miscible, yes, but not immiscible. Immiscible, you must do by a different way, which we will discuss later. Okay. So I hope that clarify your answer. So that should be miscible only, Angel. Okay. All right. So let's take a look at this kind of case. What is happening here in a fractional distillation case? All right. So let's say imagine you have, what happened is that you have a liquid, right? Let's say we have ethanol and water. Okay. Angel, later I address your answer. Address your question, sorry. Okay, we have the ethanol and the water, right? Now, can I ask all of you, right in the group chat, who should be the first one to get evaporated or boil off here in the case of ethanol and water mixture? Ethanol, okay? So as you all know, because ethanol boiling point lower, right? So what will happen? The ethanol will actually come up first. Okay? Now, but let me give you a heads up, just in case you are wondering, is it only ethanol will come up? The answer is no. Actually, water can also come up, because right, imagine, let's say the Bunsen burner, maybe I heat up to maybe 80 to 90 degree. All right. You might tell me, oh, 80, 90 degree, yeah, you will boil the ethanol. But remember, water can also evaporate very easily. So you might end up with a situation where both the ethanol and the water come out together. All right. Now, but I want to ask all of you right now, right in the group chat, then how does the fractionating column resolve this issue? How do I only end up getting ethanol only at the end of the day? Anyone got an answer to this question? How does it make sure that only ethanol at the end of the day get collected? Okay, very good. Ariel and Venice, right? Okay. Who's the face? Okay. Okay. Okay, most of you may kind of understand what's the purpose of the fractionating column. Very good. Okay, so just to give you all kind of a summary of what you all have answered to me. Okay, so you all mentioned, right, the fractionating column, right, has this very special thing inside, and that special thing is what we call beads. Okay, so I just let you all know, fractionating column, right, got they have shells, and that shells, right, actually contain the beads, right? And most of you mentioned these beads, right? What is it for? Is to provide surface area, increase in surface area in this case, right? Okay, so let me write it down here. So is to provide a larger surface area. Okay, now, but for what? That's the question, right? Is to provide a large surface area for the vapor of the liquid that have not reached their boiling point to condense and fall back into the round bottom flask in this case. So let me kind of explain this idea. So remember just how we say, right, both the ethanol and the water will come out, right? Ethanol and water will come out. But what happened? The ethanol, the gas, what happened is that it will condense, it will still condense, but it will keep repeating, it will repeat, it will get vaporized and condense. All right, condense. And then the process keep continuing on like that. Vaporize, condense until it reach to the top. Until it reach to the top, then at the top, what happened? Then after that, the ethanol will just escape and then be collected as a distillate. Then, but what about the water? The water will condense, but it will drop back inside the flask. That's the thing about your fractionating column. So take note, fractionating column, the purpose is to ensure efficient separation of the substance in this case. So to make sure the one with the lower boiling point will go up first, but the one with the higher boiling point will fall back or will not go up as far. Okay, so this process will continue, vaporize, condense, vaporize, condense, vaporize, condense, vaporize, condense. And that's pretty much it. Fractionate column. Okay, so Angel asked me a very good question. Sorry, let me pull back up. Angel asked me, is simple distillation possible for solid liquid mixture? The answer is yes, but the solid, right, must be soluble in water. That's the important thing. Okay. Okay, very good. So that is pretty much it for fractionating, fractional distillation. So fractional distillation, the only difference is you have this fractionating column. The fractionating column is to ensure that you separate the mixture as much as you can. Those with the boiling point. Okay. Yulin asked a very good question. Why water will rise up, right? It's because I remember, let's say maybe the Bunsen burner I set at 90 degrees. Now remember, water can evaporate very easily. That's how your puddle of water after the rain, right, disappear because it evaporates. So even if you never reach the boiling point of water yet, right, the water can still evaporate in this case. Okay, I hope that answered Yulin's question. Okay, anyone, any questions, clarifications? Okay, all right. If there is no more clarification, let me move on to the type of question they like to ask. This is the part that tends to make students a bit more confused, the type of question, okay? So if you all flip to the next page, so anyway, before that, I just want to really explain to all of you. So some examples that you might want to take note is to separate ethanol from ethanol water mixture, is what we went through. Other cases, right, is to separate like crude oil or petroleum. So this one is, you all haven't learned it yet. It's probably you only will learn it in Sec 4, but crude oil or petroleum is just essentially the oil that you know, like certain countries in the Middle East or Canada, right? They have oil under the ground, all right? So the oil, right, can be separated after that. And then also we can separate liquid air. Why? Because air contains nitrogen and oxygen. So sometimes if you want to obtain the pure oxygen that for, you know, for hospital to use, we have to do this way, liquid air, okay? Separate them by fractional distillation. Okay, so now let's take a look at the next page. This is the one I want you all to put a star. Very, very, very important, this question. Okay, so very typical type of question. They will ask you, okay, now I want you to sketch or tell me which graph would you obtain if, let's say, I'm trying to separate ethanol and water, right? And this temperature, right, will be the thermometer reading in this case. So everyone think is the thermometer reading. So what do you expect to see during the fractional distillation, the thermometer reading in this case? All right. So there will be two kinds. They will ask temperature against time and volume of distillate. So everyone please be careful. Distillate. Distillate is the liquid that you're collecting. Liquid collected. Against temperature. Same thing, thermometer reading. Okay, so now let's say I give you example. Maybe inside this mixture of the ethanol and water, right? Let's say maybe I have 40 cm cube of ethanol and maybe 30 cm cube of water in this case. Okay, let's say give example. All right. So what will happen to the thermometer reading as you heat it up against time? So as you allow the process to happen, right? Okay, let's say initially, start at 20 at room temperature. Okay, so obviously what happened? When you heat it up, the temperature will slowly rise, right? Okay, so let's go up. Then what happened? After that, it will reach, as what you all told me just now, right? Ethanol will be collected first. So what happened to the thermometer reading? The thermometer reading will go to 78, right? Then it will remain constant there for a few minutes. Why? Because, take note, at the 78 degrees Celsius, that is the boiling point of ethanol, right? This is where the ethanol is being collected. So it will take some time because you can see I told you all 40 cm3 of ethanol. So 40 cm3, it will take some time for all the 40 cm3 to come up and be collected as this displayed. So there will be certain time where the temperature will remain constant. Okay, everyone please take note. All right. Now, then what happened? After all the ethanol is collected, then the temperature will again rise, right? To, 100. Because why? That is the next thing we are collecting, which is the water. So it will reach to 100 degree now. Then again, the temperature remain constant. Because why? Now the water is being collected. In this case. Okay? Yeah, so that is pretty much it for the graph. So of course, right, if you continue to heat, then maybe the temperature go up. But after that, you shouldn't have anything in the flask already. So the flask will just become very, very hot. That's all. Right? So this is a very simple temperature against time graph. Okay. Anyone who is not clear how I got this graph? Or any clarification? Okay, can. Okay, I hope that's clear about this one. Okay, so this one, right, I think most students are able to do. I think if you understand the idea of what happened during the whole fractional distillation, they will understand what is happening. Now, the difficult one is the second one, is the volume of distillate collected against time. Not time, sorry, temperature. Okay, so same thing. Let's say originally we start with 20 degrees. So 20 degrees, I would say around here. So what will happen? The temperature will rise all the way to 78, right? Because haven't collect anything. The next thing, the first thing I want to collect is ethanol. So take note, if we haven't collect anything, everyone please think, the volume should be 0 initially. All the way to 78 degree. Like that. Right? Because ethanol haven't come out yet from 20 to 78. Only at 78, what happened? Then you start to collect your ethanol. So everyone please think, at 78, the graph will go up straight like that. And as what I mentioned to all of you just now, ethanol, right? How much do I have? 40 cm3. So I will collect all the 40 cm3 of ethanol at 78 degree. Okay, so let me write here. Ethanol is being collected also. Okay. All right, everyone okay? So far, I hope. Okay, then what happened? Once all the ethanol collected, right, then what happened to the temperature again? Temperature will rise to 100 degree, right? Because of the water. So again, what happened? From 78 to 100, nothing is collected. So it's flat also. Like that. Until 100. Then at 100, we will collect the water. So the water, Shavani, actually not really because try to follow how your math axis will look like So 0 will start at the origin preferably, okay? So the water will be collected. So try to use like a pen or a pencil that is a bit thicker. Then you can draw like that. Okay. So you will collect water. But water, you only collect 30 cm3. Okay, because water just now I say 30, right? So that means the final volume here will be 70 cm3. Like that. Okay, so this is where water is collected. Okay. Maybe I should write the number 30 cm3. All right, and then this one 40 cm3. Something like this. Okay, so this is the kind of graph they like to test. Okay. Yulin asked a very good question. Yulin asked, right? Why is it that once we have collected ethanol, we cannot just collect the remaining water from the original flask? Okay, technically, Yulin, you are correct. You can do that, to be honest. It's not wrong. But how to say, the example I gave you here, right, is only you have two liquids in the mixture. But what happens if, let's say, your exam question got multiple liquids, maybe got 3 or 4 or 5? So it depends on the question lah. For this one is because it's just two liquid, so we are just looking at the two liquids only lah. Okay. Yeah, but you are not wrong lah, to be honest. Yeah. Okay. Anyone got any other questions? Okay. Give you all some time to give you a few seconds to process what is happening here, the graph. Okay. If there is no more questions, we'll move on to the next few parts of your liquid-liquid mixture separation. Okay, so I forgot who was asking me just now. I think maybe Angel was asking, right? Angel was asking, right? Distillation, simple distillation, right? And fractional distillation, it is only meant for miscible miscible liquid, or essentially mixtures that can dissolve in each other, essentially, right? Now, what happens if, let's say, the liquids are not miscible, meaning it is the opposite, immiscible. Now, one of the classic example that I think you have seen before is like your oil and your water. Your oil and water, right, cannot mix. That's why we call it immiscible. So for the pure chem student, please take note, if it's immiscible, you need to do by what we call a separating funnel in this case. Okay. Oops, sorry. Give me. I'm not sure what's wrong with my iPad. Okay. So yeah. So immiscible liquids, take note. Oh, sorry. Ella, the answer is it will be a vertical line up. Okay. Not slanted. It will be vertical. Because if you tell me slanted, means you are collecting at different temperature. That's not correct. So it must be at the boiling point of the liquid. Okay. Okay. Okay, so anyway, as I was saying, right, for immiscible liquids, meaning liquids that cannot mix together, not able to mix together, like your oil and water, right, you have to use this separating funnel. All right, so for separating funnel, very easy. What happened? You will see two layers. Let's say the top layer, oil, the bottom layer, water. Then what happened? You just need to open this tap. Open the tap. Then what happened? The water will just drain. Then you collect by using a beaker or a flask, and that's it. So once you open the tap, you let this water level go all the way down, and then you are essentially separated water and oil. That's all. Okay, so that is the only example you all need to know, water and oil. But of course, exam can test other cases, but they will give you some context in this case. All right, so that's it for immiscible liquid. Should be quite straightforward. Now, the more important one we want to discuss today is your very famous paper chromatography. This one got quite a lot of questions that you all need to know how to answer. Okay. Now, paper chromatography, please take note, it is a separation technique that is used to separate and identify component based on what? Based on solubility. Very, very important. So meaning whether that substance, is it going to be soluble or not in that particular solvent in this case. So just to quickly give you an idea, what are some examples in real life we use chromatography. So if I'm not wrong, the pure chem student needs to know this. So some application that you all need to know, so let me write here, application, would be, for example, right, to identify, let's say, forgery. Like for example, some people like to forge checks, sign certain things, right? Maybe they didn't use the correct or the same pen as the person who always issue the check. So forgery in bank notes all this . Okay, bank notes, checks, all this. Okay, other cases is to detect, let's say, drugs in blood and urine . Okay, so sometimes we do that with chromatography. So you just need to know some application in real life. Okay, now, so what are some features of your chromatography that you all need to know? Okay, so if you all take a look at this diagram here, Number one, of course, you must have the solvent. Oh, sorry, I think the solvent shouldn't be here. Should be here. This is the solvent, okay? Everyone take, So you must have a solvent. The solvent can be anything. It can be water, it can be ethanol, etc., etc. Then we have this, what we call your chromatogram or chromatography paper. And then we have the start line here, all right? And then what happens, solvent front is where the solvent stops, essentially. Okay, they will stop. Okay, so you let the solvent go up until you stop, in this case. All right, that's the idea. All right, now, so what happened here, right? Take note, everyone. If let's say your aim is to find out, whether this substance maybe contain some, toxic material, or, maybe some dye that maybe not safe. So you might have seen some news, right? Some food, they recall it back because, right, not very safe for consumption. So we want to detect whether, so what happened, right? Maybe dye 1, dye 2, dye 3 are known, they know that this substance are toxic. Then what happened? This is the sample. We test it, right? Sample. And then we go and separate them. Okay, then we will see lah. Okay, we match. Okay, oh, this mixture got dye number 3 and dye number 1. So meaning this maybe this sample not very safe to consume, right? So once you maybe, let's say, a dye 1, dye 2, dye 3 are all toxic, right? Once you have it, means not good already lah. So that is how you tell, right, from your mixtures in this case. So of course, I know this is about pen ink lah, but I'm just giving you some example. Okay, so what are some common questions? Oh, sorry. Yeah. Okay. Yes. So Shavani, yes, you are right. Food flavoring can be separated also because, right, some food flavoring got color ma. So when you got color, you can separate it by chromatography. So usually chromatography is usually used for colored substances, but of course, we later address what if, let's say, it's not colored lah. Okay. All right. Okay. So think as what I mentioned, chromatography is used to separate substances because they have different solubility. What do I mean by that? Now, if you take a look at this picture here, you can see, right, I'm not sure whether your notes are colored, but if you look at my picture here, right, there is the red and the blue dye, right? Detect drug, sorry, Angel. Yeah. Okay, red and blue dye. Right? Can I ask all of you, who is more soluble here? Is it the red or the blue one? Can you all type in the chat? Okay, very good. Everyone gave me the correct answer. Take note, if you travel further, means you are more soluble. So everyone think, the red is more soluble. So because why? What's called? They travels further in this case. Okay, that is how you read your chromatography. Travel further will be more soluble. Amelia asked a good question. Will we be required to draw the different separation technique? Yes, you are required to know. Actually, sometimes they can ask. So for the pure chem student, right, sometime later on in next year, you all will do planning question. Planning question also you need to draw. Okay, just to let heads up. Okay, yeah. Okay, so anyway, moving on to a few questions that they like to ask about chromatography. Number one, they like to ask you, why do you think when you draw the dot at the chromatography, everyone think you cannot draw too big like that? Why is it like must be a small dot? Anyone can give me an answer in the group chat. Why cannot be too big, the spot? Anyone got an answer to this? Not really. Okay. Cannot separate. Okay. You must you other yeah. Color will be very faint. Okay. So most of you got the general idea. Okay, which is a very good thing to see lah, right? But let me tell you what are the things that we have experienced lah. So for me as a chemist, right, we have done all this in lab. Okay. So if you draw too big just to let you all know what happened it will spread like that outward, not very straight line but it will go outward. Not very good because right then some of the spot will be small here, but then become very big blotch here. Not very good. Okay, so this is to prevent what? Is to prevent what we call outward, the spot from spreading outwards in this case. Okay, prevent the spots from spreading outwards. Okay, so we want to be as nice as possible lah. Okay, outwards in this case. Now, as you all know by now, I think you all should know by now, solvent, take note the level must be below the start line. cannot be above. Now, a lot of students will ask me, why cannot be above? Let's say this is the spot, right? Then the water level is here. They cannot, because why? Then the sample will just dissolve in water. It will not go up. It will just dissolve. So if the start line is above, the sample will actually dissolve in the solvent. Okay, it will not go up. It will just remain inside the water or the solvent. Okay, now next question. Everyone, please type in your answer. Why do you think, okay, anyway, the start line, as you all know by now, draw with pencil. Why must be pencil and not pen? Can you all type your answer? Okay, okay, okay. Yep. Okay, very good. Okay, so most of you gave me the idea correctly. So pencil, if you use pencil, it doesn't contain dyes, right? So pencil will not separate along with your whatever sample you're trying to test, right? So if you use pen, what happened? Pen contain dyes, so the ink dyes will be in the pen will be separated along with the sample. Okay, let me write. Along with the sample. So this one not good lah. If your aim is to find only about the sample, the ink will disturb it or destroy your analysis. Okay. All right. Now, two more questions before we take a look at other things. Okay. This one, right, we will often say, right, tell students that, okay, when we do the separation, right, with your chromatography, right, you must allow the solvent to travel as far as possible in this case. What do I mean by that, right? It means, let's say, imagine your paper very long, let's say about 10 cm, right? But some student, when they do chromatography, what happen? They will stop at around halfway mark. And then they say, oh, this is the solvent line. All right? In the solvent front, sorry, not solvent line, solvent front, right? This is not good, because what? Take note, if let's say the sample got so many dots or spots, right? What will happen? It will start to overlap each other like that. This is not good, so we don't want that. So we will try to make sure you want to separate, you separate until close to the end here, solvent front, so that the spots are very nicely separated like that. Okay, so everyone think far apart as possible to ensure complete separation. Or you can say prevent overlapping of the spots. Prevent overlapping of the spots. Okay, anyone got any questions with regards to this one? Okay, I hope it's okay. Okay, so just to let you all know, sometimes we might put a lid on it, all right? Because sometimes, the solvent, right, may not be like water, right, can evaporate very easily, right? So we don't want that. So it's to prevent the solvent from evaporating in this case, okay? And lastly, a very, very, very important question. This one, I want to ask all of you. Let's say, for example, I did do a chromatography separation, right? Okay, let's say I did it in water, for example. Okay, imagine this is water. After I allow the water to go all the way up here, then I realize there's no spot left. So can anyone give me a reason why maybe this kind of case, right, will happen? There is no spot appearing. Okay, Shavani, you can? Okay. Jessie, very good. That's the answer I'm looking for. Yes, very good. Trisel also. So everyone take note, is because number one, it could be because the sample is, or the dye that is inside the sample, right, is insoluble in the solvent. So if it's insoluble, it will not go out with the water in this case. That's why most of the time, sometimes you might want to adjust your solvent. Maybe instead of using water, maybe you want to use other solvent like ethanol. Then in ethanol, maybe can see. So let's say, for example, this sample X, right, in water, but the same sample X, but now in ethanol. Then you maybe can see the spot like that. So then we can say, oh, okay, this spot only soluble in ethanol. Something like that. Okay, so this one, everyone please take note, very important. They sometimes will ask you this kind of question. Okay, very good. Everyone managed to understand what's happening here. Okay, now, so that's the main bulk of the chromatography that you all need to know. All right, now, for the pure chem student, please take note, you also need to know other things with regards to chromatography. Now, there is this thing, what we call retention factor or RF. So I think for the pure chem student, you will have learned this. Now, what is RF? Now, what are the solvents that we... Oh, okay. You asked a very good question. What are the solvents that you need to know for paper chromatography? Most of the time, the basic one will be just water and ethanol. I think that's the two that you would need to know lah. But of course, in your exam, they can test other solvent lah. Then you just follow the storyline given to you. Okay. Okay. But water and ethanol will be the two common ones. Okay, so as I was saying, right, for retention factor, now retention factor, right, is just a math problem, okay, just to let you all know. Now, so for those pure chem students, please take note, retention factor, how do we calculate the retention factor? It is it's like a ratio. It is the distance traveled by the sample or the spot, right, over the distance traveled by the solvent. That is the formula to calculate RF, right? It is the distance by the solvent. Distance by sample over distance by solvent. Now, but here, I want to warn all of you about RF formula. Where do you calculate or you measure the distance starting from where? You must start from the start line. Start from the start line. So when you calculate your RF, please be a bit careful. Imagine this is the start line. Please do not include this 1 cm. It will be marked wrong. You start from the start line, then you measure from there to the solvent front. If you are finding the distance traveled by the solvent. All right. So take note, if let's say if you look at my picture here, you can see the distance traveled by the solvent will be 6 cm. This is the distance by the solvent. Because it stops here at the solvent front. Here. Then how do you find the RF of, let's say, the different dyes, right? Let's say, for example, yellow color dye here. To find the RF, it will just be 3 divided by 6. That's it. Then it will be 0.5. But for the orange spot, it will be, RF is 4.5 divided by 6, which is around 0.75. Very simple. The RF value, you just need to calculate by this way. So just be a bit careful. Choose your distance carefully in this case. All right. Now, obviously, I'm not sure how your teachers actually explain to you. Okay, I'm not sure they got explained to you why RF is so important, right? Now I'm going to go through with all of you. Very important. Okay, anyway, take note, RF, right, will be different for different substances. Now, but take note, it is also different if you use different solvent in this case. All right, so everyone please note, they are the same for the same solvent. All right, and the value will be different if you use different solvent. All right, so be careful. Okay, so Jaslyn asked a good question. Is it RF in 1 decimal place? That depends on your school. Some school, they want the 1 decimal place. Some school, 3 SF and whatnot. So just follow your school. Okay, for O level, they are not very clear about this. Yeah. Okay. All right. Okay, so everyone take note, it is the same for the same solvent, but different for a different solvent. Now, why RF is so important, right? Let me give you an analogy or to kind of give you an idea, okay? Imagine I told you, okay, I give maybe someone, right, in this class, right, a sample X. This sample X, I try to separate, okay? I do by chromatography. Maybe in your lab, right, maybe you all not so rich. Let's say very poor. Maybe the paper only 10 cm only. Okay, let's say 10 cm. Okay, 10 cm. Or maybe I start from start line. Okay, let's say that this is 10 cm, right? Okay, then what happened? I sample the X. And then I found, oh, X travel maybe about 3 cm. Okay, then I calculate, okay, RF of X is 3 over 10, which is 0.3. So in my lab, I know, okay, the RF of this X is 0.3. Now, but what happened? If let's say another scientist in another country did this sample also X, but maybe that country more rich. So the chromatography paper even longer, let's say like that. Maybe 20 cm, for example. What happened? Then his sample, right? Can I ask all of you in the group chat, will it also travel by 3 or not in this case? By 3 cm? No, it will be, Chloe give me the correct answer. The answer is no, it will be now 6 cm in this case, right? So it will be 6 cm. So because, right, if you didn't know this RF value, some people will tell me, oh, this sample is not the same. But that's why RF value very important because, right, it will tell you, okay, this sample X have an RF value of 0.3. So we will then be able to tell what is the distance depending on the paper length you all use in this case. So the RF value will always be 0.3 is a matter of what is the length of the solvent front you use in this case. So some scientists might say, oh, different substance because the distance travel is different. Wrong. It's because the RF is the same, they should be the same thing. Okay, so just to give you an idea why RF value is important here. Okay, all right, so that's pretty much it for RF value lah. So you just need to know how to calculate. You need to be able to identify the substance based on the RF values in this case. All right, and lastly, I think I forgot someone gave me another answer for the, what if let's say the spot is not visible, right? For those that are colorless, as you all know by now, you need to put locating agent. It is to detect colorless substance in this case. All right, so that will be your locating agent in this case. Okay, so I'm pretty much done with the separation technique. All right, so everyone who is in the group chat have problem with separation technique. Oh, gas separation, usually you all don't learn for the syllabus. Gas separation, usually I just let you all know. So Shihan is asking about gas separation. Gas separation, right? There are different ways of doing it. One way is do by fractional distillation, right? But the gas, right? What happened? We will condense it into liquid first, then we will do fractional distillation. Yeah. Okay, Chloe asks, but wouldn't there be substances with very good question, Chloe. Yes, to be honest, right? There might be some substances, the RF value might be similar. But think, maybe in water. But let's say if we do it in ethanol, maybe it's different. So that's why we will try it with different solvent to make sure that the RF value is as different as possible. Okay. Okay, any other questions before I move on to kinetic particle theory? Because that one is quite straightforward. Okay, can. All right. So that is pretty much it for separation technique lah. Okay. So for the questions, right, please go and try lah. Later I will give you all the answers to the question. Okay. All right. So now, right, let's move on to separation technique. So everyone, please flip to what page is this? Page 23. Yeah. Okay. Okay. Everyone okay? I hope. Okay, so for kinetic particle theory, I will quickly run through some of the important concepts. Because technically kinetic particle theory, I think most of you in lower sec you have touched it. It's just that maybe there are some new stuff that you all must take note lah. So I will go through the new stuff. Okay. All right. So for kinetic particle theory, as you all know by now, you all learned the three states of matter. They are solid, liquid, and gas. All right. Now, take note for kinetic particle theory, the type of question we always ask is this. They will ask you, okay, what is the arrangement? What is the, what's it called? The movement of the particles in this case. So please take note. Try to find a way to remember how you answer your question. So of course, right, some school will have a different way of phrasing your answer. So if your school requires you to write the way they want you to write, please go ahead and write. So for me, for arrangement, number one, please take note, for solid, right, must be very closely packed, orderly arrangement. Liquid, closely packed, but disorderly. Gases, far apart, but disorderly also. Okay. Now, then for movement, solid, vibrate in its fixed position. Liquid slide, but gases move freely in all directions at high speed. So that is how usually I will phrase my answer lah. All right. So if you are kiasu, write the whole thing. All right. So I will leave it to all of you. Okay. Now, but what other important things you need to take note? Number two, right, is actually the forces of attraction. Now, for those who are not very familiar with forces of attraction, right, you can think of it this way. Forces of attraction is just means, imagine one particle, they are trying to attract the other particles around it, essentially. So forces of attraction is just meaning they are trying to pull the particle together as close as possible in this case. All right. So for solid, right, as you can see, the arrangement are very closely packed. That means the forces of attraction is very strong because they can pull each other so closely. But for liquid, right, still closely packed, but not as close, right? So we will say just strong or moderate in strength, okay? And then, but for gases, you can see they are so far apart to each other, the forces of attraction is very weak in this case, right? So these are important things about the forces of attraction, right? And lastly, for compressibility, I think you all learned before, solid and liquid cannot compress, but gases can compress. Now, anyone in the group chat can tell me why gases can be easily compressed? What's the reason, if I ask you? Okay, so because as what some of you say, no fixed shape, they are far apart. The one that Ariel gave me is the one that we are looking for. You need to say because there is a lot of spaces between them, between the particles. So that's why, in this case, they are easily compressed. You can cause the particle to come closer. Okay, very good. Okay, so that's it for this one. Okay, now, so then after that, what happened? Then you also learn the 3 states of matter, as you all know by now. All right, you have the melting and boiling, freezing, condensation, and sublimation. So for all of you to take note, deposition is not in your syllabus, but if you want to take note, just take note. It's not in the syllabus. Okay, so what are the important things I want to emphasize here? Now, melting, boiling, and sublimation, everyone please take note. All right, is to convert from solid to liquid, liquid to gas, and for sublimation is from solid to gas directly. All these processes, right, you will absorb energy or heat energy. Okay, so I think you all can see in the notes here, the red color, they all absorb energy. But condensation and freezing, they all release energy in this case, or lose energy. Okay, but later we will explain why this is important for some of the questions in this case. Okay, so that's pretty much it for the change in state. All right, so this one for evaporation and boiling, I will let you all read. But sublimation also, we just went through just now. What are some examples of cases that undergo sublimation? So we just mentioned dry ice, mothball, all this. Okay, so the one that I want to talk about today is this one. This one very important. They like to test this. Okay, so let's take a look. Imagine, let's say, initially you started with some ice. And the ice, maybe the temperature, let's say we start with around -20 lah. Okay, let's say the ice. Okay, then what happened? The ice, you decided to heat it up. So you all know lah, what happened to ice, right? The ice will start to melt in this case. So imagine you put a thermometer here, and then you measure the temperature lah, as the ice is melting and whatnot, right? Okay, so you all can see from the temperature, right? The temperature will rise from -20, and as you all know, the melting point of ice or water is around 0 degree in this case. Am I right? Everyone okay? Okay, then you see something very weird about it, because right, at 0 degree, suddenly what happened? The temperature suddenly remains constant. Because why? Take note, when temperature remains constant, that will indicate to you that melting has occurred here. Okay? Very important. So this part here, when the temperature remains constant, that will tell you melting has occurred. Now, after melting has occurred, right, what happened? Obviously, at some point, all the ice will have melted, right? Once the ice has melted, at point C is where all ice melted, then the temperature will start to rise again. So what are the important things you need to take note about this kind of question or this kind of graph, right? Number one, you all need to know is you must tell me that this is what is happening. Melting is occurring when temperature remains constant. Okay, number two, they will like to ask you, what is the physical state of the ice or the water, right, at those temperature? So as you all know, from -20 to 0 degree, they should exist as solid still because they are still ice, haven't melted yet, right? So everyone take note, from A to B, they should be solid. But what happened during melting? Melting, right, is when you are melting the solid ice, right? The solid ice is turning into your liquid water. So during melting, everyone think you have both solid and liquid water. So solid plus liquid. Okay, because they are in the process of melting. But after all the ice melt, what happened? When temperature increase again, that is where your liquid water will be present in this case. So from A to B solid, B to C solid and liquid, and then C to D liquid water. Okay. Now, but the third question they always like to ask is this. Why does the temperature remain constant during melting here? So this one, everyone please put a star. They will ask you to explain why temperature remain constant during melting. All right. So let me go through. Very important. Right. Now, just now we clarify a few things about solid and liquid. Right. Now, imagine the solid particles, right, originally are very closely packed in a very orderly manner like this, right? Now, what do you all think? And this one you all can write in the group chat. What do you think they are doing with the energy that they're absorbing here? In this case. Okay. So Jaslyn. Okay, very good. Jaslyn gave me the correct answer. So think now, what happened? My aim is to melt the ice, right? Solid become liquid. Liquid now closely packed, but not in orderly arrangement, right? Not as nice. So what is the energy they are doing here? What they are trying to do with the energy? The energy is used to overcome the forces of attraction between the particle, so that the solid particle will now become like liquid. Not the force of attraction, not very strong already, cannot pull together that easy. So everyone in note, energy is absorbed is used to overcome the forces of attraction between the particle. Between, if you want to be a bit more specific, solid particles. Like that. Instead of increasing the temperature, the energy they absorb is to overcome the forces of attraction. In this case. Okay, so that is melting. So meaning similarly, what if let's say the water, right, after you melt become water, right, you continue to heat, right? You increase the Bunsen burner temperature to let's say 100 degree. Now, as you all know, okay, water boil at 100, right? So meaning the temperature rise until 100 degree here. Then what happened? Then temperature again remain constant. Because why? This is where boiling will start to occur. So everyone think boiling. Later we discuss that, Xander. Because I think there's a question at the bottom. Yeah. Okay. So it will boil, right? Then what happened? Then the liquid, right, water is changing to gas, right? So during boiling, you have liquid plus gas. But after 100, once all the water gone, become gas already. From E to F. Okay. So let me write here. Liquid plus gas. And this is gas in this case. Okay, I'm so sorry. I will extend the lesson a bit. So if let's say you all are in a rush, you can leave first. Okay, I will extend the lesson, okay, so that at least I can cover the content that I need to cover today. Okay. Okay, now, so again, you realize, right, during boiling, what happened? Temperature again remain constant. Because, right, same idea. Your aim is to convert from the liquid, right? Liquid is closely packed, but not so nice arrangement, to become very far apart. So why? Again, because we need energy to overcome the forces of attraction. Same reasoning. Overcome the forces of attraction between the liquid particle. In this case. So that it becomes a gas particle. Okay, so those are the common type of question they will ask. Why temperature remains constant? Okay, anyone have any clarification you all want to see? Yeah, if everyone is okay, let's move on to the last type of question they like to ask. Now, confirm there will be one question they will ask you. Okay, what happened to the arrangement and the movement of the particle from A to D? They always ask you this kind of question. So A to D, just now we've already mentioned, right? A originally is solid. Then D, right, is still technically liquid, haven't boiled yet, right? So meaning your answer must talk about changes in the arrangement and movement from solid to liquid. Okay, so that's why at the front part of this topic, right, take note, I mentioned about the arrangement and movement. Very, very important. You all must hit those points when you explain the changes. So how do you explain? Number one, of course, let's do point by point arrangement. You will say that the particles, the arrangement of the particles, let me write, arrangement of the particles changes from very closely packed in orderly arrangement to closely packed but not in or in disorderly arrangement. So these are the points we are looking for 1 mark. So usually this kind of question are 2 marks. So you must tell me how the arrangement change. Very closely packed, orderly. This is solid. To closely packed in disorderly, liquid. For 1 mark. Okay, then the other mark is movement. Okay, so how do you say about movement? So let me write here, movement. Okay, so the movement of the particle changes from vibrating in its fixed position to what's it called? Sliding over each other. Okay, so same thing. Solid is vibrating in its fixed position to liquid is sliding each other. Okay, why can't particle change temperature and state at the same time? Sorry, eventually, I don't really understand your question. What do you mean by change temperature and state at the same time? Wait, let me try to understand your question. Change temperature and state at the same time. Oh, like the temperature increase, yet the state changes. Oh, okay. Be careful. Okay. So eventually asked a very good question. Maybe I should clarify that. Now, eventually is asking, right, when the temperature increase, right, does the so-called the state changes at the same time? Okay. So be careful. Take note. Now, when the temperature increase, right, meaning sorry, I know some of you are still copying, but give me a minute. So what happened? When temperature increase, right, from here, here, and here, right, take note, there is no change in state. Meaning at this point, from A to B, it is solid. C to D, liquid. E to F is gas. No change in state. The change in state only happened during the melting and boiling. And how do you tell melting and boiling? Is when the temperature remains constant. Those are the important things you need to take note. I hope that's clear eventually. Okay. Yeah, so there is no such thing as temperature increase means change in state. There's no such thing. Temperature increase is just temperature increase. But when there's a change in state, right, temperature remain constant. Okay, I hope that's clear eventually. Yeah. Okay. Amelia asked a very good question. Okay, what's the difference between molecule and particle? This one I think you will learn later on. But essentially, what particle mean? Particle, right, is a very generic term. It can refer to atoms, molecules, ions, etc., etc. So particles is about a bit more broader. Molecule very specific so it's only for certain cases we refer that as molecule. So if you want to be on the safe side right now for your WA1, just say particle to be on the same side. Is the liquid is the same temperature as the solid? So when it melts, the liquid is the same temperature? Yes, correct, Chloe. So during melting and boiling, the temperature must remain constant. That is where both the solid and the liquid exist at the same time. So during the process of melting, right, same temperature. But once all the solid, right, these have melted, then the temperature will start to increase after that. Okay, all good, very good question. Don't be afraid to ask. Okay. All right. Any other questions? Clarification? All right. So that is it for heating curve. So heating, right, it just means you heat the solid to become liquid and gas. But read your question carefully. Sometimes the question like to trick students. Maybe doesn't start with solid. Maybe start with liquid. So please read the question carefully. Okay. Now, of course, right, we have the opposite scenario. The opposite scenario is what? If let's say we cool it, right? So now let's say we have a cooling curve. So again, imagine you start off with let's say water vapor. Water vapor, temperature about 120 degree, your steam, right? So then I put inside the freezer, for example, right? So in the freezer, it will start to cool. Now, as you can see, the temperature again will start to drop. So as it drop, right, same thing for your water, right? What happened? You all learn freezing, sorry, not freezing. The what's called boiling point of water is 100. You can see temperature remains constant, right? And then you can see what happened. It will start to condense. This is condensation will occur. Condensation. Okay. So what happened to the gas? The gas in the condensation state is both gas and liquid. All right. Then once all the gas become liquid, then you continue being a liquid after that. All right. So let me write here. So gas plus liquid. All right. And then this is liquid. Okay. Same idea. It's just the opposite way. Okay. From gas to liquid. Condensation. All right. So condensation occurs. Okay. So now the question is this. This one I want to ask all of you to write in the chat. Why do you think temperature remain constant during condensation this time? Because this time round, I'm not providing heat like just now. The heating curve is you heat up the liquid or the solid, right? But this time round, I'm cooling it. So anyone know why the temperature remain constant during condensation? Yes, very good. Justin gave me the correct answer, but I want to see the rest. Anyone got any other answer? Why temperature remain constant? So usually a lot of students when we ask this kind of question for the cooling curve, they usually give the correct they don't really understand what's happening here. So imagine originally gas, right? Remember, it is very far apart from each other. But what happened? Now I want you to convert to liquid. Liquid now closely packed, right? So what are we doing here? We are increasing the forces of attraction here. So remember, I mentioned just now, force of attraction is all about pulling the particles together. So take note, the energy in this case is released because why? Due to formation of the forces of attraction between the particles in this case. So this one, a lot of students don't know how to answer. So make sure you are clear now. How do you explain this one? They are trying to form back the forces of attraction in this case, not to break it. Okay, so that is what's happening in condensation. Okay, and then process will continue on. So if let's say you continue to put in the freezer, right? Then as you all know, then the liquid water will start to freeze at 0 degree. So this is freezing. All right. And then it will continue to become solid. So this one freezing become liquid and liquid and solid, sorry. And then once you freeze, become solid. Okay. So liquid plus solid. And this one solid. So the reason is the same. Why temperature remain constant during freezing is because formation of the forces of attraction. Okay. Everyone okay with regards to this one? Okay. So that's it for the cooling curve. Okay. So as per usual, the question will ask you also, what is the change in the arrangement and movement from this state to this state? So if you look at the graph from P to S, P is a gas, S is a liquid, right? So you need to tell me what is the change from gas to liquid in this case. All right. So the answer, as per usual, number one, the arrangement of the particles. all right, changes from very far apart in disorderly manner to closely packed in disorderly manner. Right? Then for movement, you will say movement of particle changes from movement will be what's it called? From very high speed in all direction to sliding over each other. Okay, okay. All right, then you'll copy down first the changes. Okay, so sorry, give me about 10 to 15 minutes to wrap up the rest of the content that I need to go through lah. All right. Then later I will give you all the link to the answers to the questions. Oh, okay. Hold on. Give me a minute. Okay, so that's pretty much it for the heating and cooling curve. All right, so to make things faster, let me quickly go through what are the things you need to take note about this particular topic lah. Okay, now so for everyone, please take note. Why is this graph very, very, very important? You need to know this. The temperature remain constant part is because so just now we went through about mixtures, right? Mixtures we learned, right? They are made out of two or more substances that they are not chemically combined. Now, how do you identify whether a substance is a very nice pure substance or a mixture? So take note, you all must know the difference. Pure substance, right? The melting and boiling point is fixed. Meaning, water, for example, boiling point 100, what's called? Melting point is 0 degree, fixed. But once, let's say, if you sprinkle a bit of salt into the water, right? Take note, the melting boiling point, they will melt and boil over a range of temperature, actually. Okay, so if you look at the graph at the bottom, you see what happened. Originally, pure substance will be flat. All right, the temperature. So this is for pure. But if you are impure or a mixture, then you see the melting boiling point is no longer flat. It will be a range. So meaning maybe water, this one is what melting point 45, right? But then when you sprinkle a bit of other impurities, the melting point will be a range from 40 to 50, that kind. So please take note, this is how you tell whether the substance is pure or not pure. This is your exam question also. Your exam question, they like to ask you whether is it pure or impure based on the graph. Now, so as you can see here, to test whether a substance is pure, right? Everyone please take note, you must test for melting and boiling point. This is very, very important. Okay, if you want to test or to check whether a substance is pure. Okay, so that is the important thing here lah. That's pretty much it. Okay, all right. So I'm pretty much done with the stuff here. Now, so for any combined science student, right? If you want, you can leave already. I will if you want, let me send the answer because the next part will be actually for the pure chem students only lah. Yeah, let me send the answers just in case you all need the answer. Give me a minute. Okay, yeah. Okay, give me. Okay, hold on. Okay, so for you, if for the combined science, you are done already lah. But for the pure student, you can stay back. We will talk about one more thing. So for the pure chem students, right, you all need to know the last thing is diffusion lah. Okay, now I think most of you have an idea of what is a diffusion process, right? Now, so take note, diffusion is a net movement of particles from a region of higher concentration to a region of lower concentration. Oh, sorry. Did I send to the correct people? Sorry. I think I sent it to the wrong people. Okay, yeah, this is the answer. Okay, so what happened? As you all know, diffusion, right, can happen in a lot of situations. So one example will be, let's say, diffusion of liquid. Let's say if you mix if you know your syrup, right, your rose syrup and whatnot with water, after a while it will spread out. Right? Now, other example is diffusion in gas. Like for example, if you spray your perfume, what happened? You can smell the perfume after a while from a miles away, right? So diffusion can happen because why? If you spray here, let's say imagine if I have the bottle of perfume here, if I spray here, the particles higher, right? But in the room, on the other side of the room, this is lower. So the particles, right, will diffuse from a region of higher to lower concentration every time. Okay, so what are the factors that affect rate of diffusion? So I think the first one is pretty obvious. The higher the temperature, the higher the rate of diffusion. I think that's pretty obvious because, like, as you all know, like for example, if you dissolve your Milo powder, it's better to dissolve it in higher temperature than lower temperature in this case. So higher temperature, why? Because they possess higher kinetic energy, so therefore rate of diffusion will be faster. Now, but the most important one for all of you is this, very, very important. It is the MR, or the particle size. Now, for those who are not familiar, what is relative molecular mass? Relative molecular mass, right, essentially means it is the size of the particles. All right, and everyone please say no. How do you calculate the MR, or the size of the particle? You need to refer to your periodic table. So let me refer to all that. Your periodic table, take note, you must take the number at the bottom here. These are all the sizes of the particle in this case. So if I ask you to find the size of, let's say, HCl, then what happened? You just need to sum up the size of H and the size of Cl here. So it will be 1 plus 35.5, which is 36.5. All right. If I ask you to find the size of ammonia, NH3, this one, they will usually give you the formula because most of you have not learned the formula yet. So N is 14 and H got 3 of them. So 3 times 1, which is 17 like this. So just refer to your periodic table. You are given your periodic table, refer to it, calculate for me the size. Okay, why size is very important for this particular portion of diffusion is because, take note, the bigger you are, the slower you will run, or the lower the rate of diffusion. So for me, I'm also a big size guy. Big size guys usually run very slow, right? So you can use this analogy, very easy one. Okay. So what are the common questions they like to ask for your exam question? Like this one, very famous experiment question. They will tell you, oh, okay, I put 2 things inside this tube. One is ammonia. So ammonia, let me give you all the formula, is NH3. And on the right side, it is HCl. Okay. Then what happened? When these two, when they vaporize, right, or become gas, right, they will react, right, to form this what we call ammonium chloride. It's a compound, it's a product of the reaction. And this white film, right, you realize that it is formed nearer towards the HCl rather than the ammonia, not even in the middle, right? So the middle is around here. This is the middle. But you realize, right, it is formed closer to the HCl, right? So this is where your MR, or the size, will come in. So just now we already calculated, right? HCl, the size was 36.5 and ammonia is 17, right? So can I ask all of you, if you look at the number, who do you think diffuse at a faster rate? Can everyone tell me in the group chat? Correct, Chloe. Ammonia. So ammonia will travel further, faster, right? But HCl don't travel that fast. So how do you explain in your exam? Is this firstly, for me, I will tell student, write for me the MR. MR of ammonia is 17, while MR of HCl is 36.5. All right, be kiasu lah. I always kiasu. I write everything just to make sure we are clear. Then you will say, okay, since ammonia has a lower MR, it has a higher rate of diffusion than ammonia. Okay, so that is what you need to say. So if you want to give me a concluding statement, you can say, hence, ammonium chloride is formed closer to hydrochloric acid. Okay, so very classic question, very classic example. For the state of matter, why are the spaces between called empty spaces or vacuum? Also, are we supposed to mention terminal energy conversion to kinetic energy? Did I not write? Oh, yeah, sorry. Yeah, I should write higher rate diffusion than ammonia and hence travel further. Yeah, sorry, I forgot to write that. Hence travel further. Thank you so much. Forgot to write that. Okay, Amelia, for the state of matter, why are the spaces between? Okay, Amelia, to answer your question, right, they are indeed empty spaces because why? There is no particles between them. So if let's say you're talking about the particle, all these are empty spaces because why? There are no particles between them. Yeah, so vacuum, right, usually is referring to something or a space that contain nothing. No particle, no nothing. Are we supposed to mention the thermal energy conversion to kinetic energy? If you want, Amelia can. But that is only when the temperature is rising, not during the melting and boiling. Okay, just take note. Calculate MR. Zena asked, do we need to calculate MR or ammonium chloride? The answer is no need. Because right, the ammonium chloride is the product of the reaction. So there's no need to do that. You only do for the initial two reactants, which is the ammonia and the hydrochloric acid. Okay, so last question before we call it a day. All right, so another type of question we always ask for diffusion is the next page one, the very famous one, which is this one, right? I think most of you have seen this before, right? So they will ask you, what happened to the water level here? Here, if let's say if you look at this diagram here, inside this porous spot, it contains I think carbon dioxide. Okay, so carbon dioxide, the formula is CO2. Okay, everyone take So inside this is CO2, but inside this beaker, the large beaker is nitrogen, which is N2 in this case. Correct? Now, so take note, what does a porous spot mean? A porous spot means essentially is a pot that contains tiny, tiny holes. So these tiny, tiny holes, right, what happened? It allows the gas to move in and out, essentially. Okay? Now, so same thing for this question, the first thing I will always ask you to do, calculate the MR. So if you refer to your periodic table, let me write down for you, the MR of nitrogen is 2 times 40, which is 28. But the MR of CO2 is 12 plus 2 times 16, which is 44. Now, so my next question will be, everyone, answer, who will diffuse faster? Nitrogen or carbon dioxide? The answer is nitrogen. So you can see the nitrogen that is found outside inside this beaker, what happened? Because it diffused faster, it will go in faster. The net diffusion will be faster inside. So when you have diffused inside faster, right, what happened? The volume of the gas inside this porous spot will start to increase and it will push the water down. So the water level X here, take note, will actually be lower or decrease in this case. All right, so let me write here. So the first thing I will write is, of course, MR of N2 is 28. MR of CO2 is 44. Then what do you all need to say? Number 2, you say, since the MR of N2 is lower, it will diffuse into the porous spot. Everyone think, into the porous spot at a faster rate. Okay, so you need to tell me this, diffuse in the porous spot at a faster rate. Then what happened? So some of your school will be quite niao about this. They will say, hence, this result in a larger volume of gas inside the porous spot. In the porous spot. Or some school will say, porous spot. Or some school will say higher pressure because we got more gas. So higher pressure in the porous spot. Then what happened? You will say push the water level at X down in this case. Okay, so you tell me either got more gas inside the porous spot or the pressure become too high already. So that's why it caused the water level to go down because it get pushed down in this case. Okay. All right. So I let you all copy down for first few another 1 more minute, then we can call it a day. But before you guys go, I just want to kind of give a debriefing about the whole thing lah. Okay. So okay, give about 1 more minute to copy down. All right, so that is pretty much it for today's WA1 revision. I hope today's lesson has been pretty useful for all of you for your revision for your upcoming WA1. Now, before we call it a day, let me quickly talk about something. Then, of course, if you got any question later on, you can stay back and ask me a few things lah. Okay, so one thing I just want to quickly debrief all of you. So number one, take note the answers. I think I got sent in the group chat, but for those who miss it, you can scan this QR code to obtain the answers to the question. So please go and try. If you have any questions, do let me know lah. Okay. Now, but before that, if you want, I hope the lesson has been useful. If you are okay, you can leave a review for me. How the WA1 online revision was lah. Okay. So you can scan the QR code. Now, if you are interested to join the classes, you can always look at the OVERMUGGED what's called OVERMUGGED website to look at the schedules that we have. If you want to join the chemistry or any other subject, you can feel free to go and check the website for the lessons lah. Okay. All right. So anyway, that's it for me today. If you have any questions, you can stay back and ask me. But if not, I will see you all. Please take care of yourself. All the best for your WA1. Thank you so much. Okay. For your participation also lah. Huh? Okay.